Okay, so we have a second question on Newton's second law in rotation. So let's read the question. A sphere of radius 0.05 meters and the mass 0.2 kilograms rolls down an inclined plane without slipping. If the inclined plane is 0.3 meters tall and has an angle of 30 degrees, then how long does it take the sphere to roll down the inclined plane? And additional question, how will your answer change if it were a disk, a ring, a shell of the same radius and mass? So we're basically asked four questions at the same time. What if it is a shell or a disk, a ring, or maybe a solid sphere? So we'll start from calculating the rotational inertia, but rotational inertia requires us to define where the rotational axis of rotation is. So does torque. So I have over here a magnified version of this diagram, so I can draw the results a little more clearly. So let's take a look here. This is the point of contact between the sphere or whatever circular shape with the inclined plane. I like to choose this point to be the axis of rotation. If you have watched a previous video I recorded, this point is instantaneously at rest. So it is a very nice instantaneous axis of rotation because friction through it, well, it doesn't have any torque, right? Normal force through it, this way, doesn't have any torque. So the only force that has torque is gravity. Okay, so where does gravity apply? Near here, I hope this is the center. So gravity applies downward. So let's draw gravity. And this is the axis of rotation. The line of action is just extension line running through gravity. Okay, so we want to find the lever arm of gravity, that is the perpendicular distance between this line of action and this point, the axis of rotation. All I have to do is to draw a perpendicular line here. So right here, this short section is the lever arm. So let's maybe color it differently. Hopefully the red color will stay. Oh, see that? It went to the bottom. Color it again. Oh, went to the bottom again. Looks like it wants to go to the bottom. But I think I did it enough so that you can see this. Okay, there. Well, the computer programmer probably needs to revise that software. Okay, so we have kind of highlighted this. So this is our lever arm, and I'll call it LG, so lever arm of gravity, right there. So in this right angle triangle, I have this R radius as the hypotenuse, and this LG is the opposite of this angle. And you can find out this angle is actually related to the inclined plane's angle. So anywhere you draw a horizontal line with the inclined plane, that's that same angle there. All right, so now LG should be equal to R sine theta according to this. All right, so a tricky thing for this problem is, since we have chosen this point to be the axis of rotation, the rotational inertia of all these circular shapes will have to be rotating around this rim, point on the rim, but not through the center, right? So we need to calculate the new rotational inertia in this situation. So let's first define axis of rotation is equal to this this point. Let's call this point A is equal to this point A, so that our rotational inertia will have to be calculated using parallel axis theorem. So rotational inertia of center mass plus there's this displacement, and the displacement from the center mass, this is center mass, to this point A is a whole radius, so that distance radius squared. And I can write this as n times mr squared. This n denotes the shape. So for a disk, n is 1/2, right? For a ring, n is 1. For a shell, n is a 2/3. Where's our sphere? The sphere is 2/5. So all that matters, this number is staying as generic as possible. So now we add this 1 times mr squared, so the result is n plus 1 mr squared. And we'll have a list of values such as n equals 1, this is for ring, n equals 2, over 3, let's do that, 2 over 3, this is shell. I'm sorting these basically with a descending order of the value. So 1 over 2, this is for a disk. And then 2 over 5, this is for a sphere, which is our first question. So that's what our n is going to be in this question. It stays as a generic value. Okay, so now we can calculate the torque. The torque from gravity is equal to F gravity, lever arm gravity. So it's mass gravitational constant, and this lever arm gravity is r sine theta, and according to Newton's second law in rotation, this is the only torque. The other forces such as friction here has 0 lever arm through that axis of rotation. Normal force also goes through that axis of rotation, so it has 0 lever arm. So this instant rotational axis is very handy. So now let's equate this with I and alpha. This is how we use Newton's second law in rotation. So alpha is equal to mg r sine theta over I. Alright, so let's plug in the I's value from here, and that should cancel a few factors. So we can divide out m, we can divide out 1r, and we have g sine theta over this n plus 1r. So let's sort this out. G over n plus 1r sine theta. So now we have angular acceleration. We can relate this with linear acceleration using the A center of mass is equal to alpha times radius r. So this r relates the axis of rotation to the center of mass. The distance is exactly 1r. So now we have this r is going to cancel out, so we'll have g over n plus 1 sine theta. And I want to take a moment to compare with this A equals g sine theta for no rotation. We could have done this without the rotation, right? We could have done this with just a ball somehow slides down the inclined plane. With no friction, it could slide down the inclined plane, right? So with no rotation, we have this. With rotation, we have this over n plus 1. N is always greater than 0, so this with rotation, the linear acceleration is less than without rotation. That means if you predict without rotation and with rotation, you'll be having a less acceleration. You'll probably see a longer time to roll down the inclined planes compared to translate or slide down the inclined plane. Okay, so now that we have this, we can calculate the time. We'll set up a problem because we know the center of mass is going to do this. So we'll set up a kinematics problem with x0 equals 0 at the top of the inclined plane. X is equal to a final position, let's say a distance d along the inclined plane. We're going to calculate this out. And v0 is equal to 0, and v equals unknown. And a is equal to g over n plus 1 sine theta. And then t is equal to unknown. So we want this. We don't really necessarily have to have this. We just want the time. So how far did does the ball displace its center mass? So let's go to the bottom, top right corner. So the ball comes down here, and this entire length is related to the height. So this height h and angle theta, and this distance, let's call this distance d. So this whole distance here. So from geometry, I know that h over d is equal to sine theta, so that d is equal to h divided by sine theta. Alright, so we can use that over here in the kinematics. So this is equal to h divided by sine theta. Just trying to save some space. So let's calculate the time it takes. We just need this equation, x equals x0 plus v0t plus 1/2 at squared. Right, so we just calculate, we plug in the value. This is a 0, this is v0 is a 0, right? This x equal to that d. So we'll get something like this. So h over sine theta equals 1/2 at squared. So that your t squared is equal to h times 2, then divide by this a. So 2h divided by a sine theta, and then you can square root it, right? So before we square root it, let's plug in a's value. So a is this. So let's see, 2h, and a has this n plus 1 in the denominator, so now it flips to the numerator because a is in the denominator, and then divide it. A has this g and sine theta, and I'll have g and sine theta, but there's already a sine theta, sine square theta. That means the sine theta is squared. So now we have this as t. So we can solve for t. T is the square root of this, and the sine theta square root is out because the sine theta squared. So 2h n plus 1 divided by g divided by sine theta. And this t depends on the shape. So let's have 4 separate values. So shape 1, the ring has a 1, mr squared. So shape 1 we have 1, so n plus 1 is 2, so 4 h over g divided by sine theta, and this part is in the square root, and we can calculate. You can use your calculator. So the next one is the shell. The shell has 2/3, so 2/3 plus a 1 is 5/3. So 5/3, then multiply by a 2, so 10 over 3 h over g square root over sine theta. And the next one, the 1/2 plus 1 is 3/2, so 3/2 into 6/2, or you can say a 3. And the last one, the sphere, the 2/5, so plus 1 is 7/5 times 2. I think we just barely fit everything here. Divide by sine theta. Okay, so it's time to pause and pull out your calculator. Okay, so with a calculator, this is a ring, takes 0.700 seconds, and this is a shell, it takes 0.639 seconds, and the next one is a disk, takes 0.606 seconds, and last one is a sphere, it takes 0.586 seconds. So between fast and slow, so this is fast, and this is slow. So if you try to reach all the four shapes together on the same inclined plane, given the fact that they're under the same condition, then the ring here takes the longest time. So let's put the ring here. The ring takes the longest time because it needs to give a lot of that translational kinetic energy to rotational kinetic energy when we need to consider the rotation, because of the large amount of rotational inertia a ring has. And then progressively you have less and less rotational inertia, so the kinetic energy due to rotation is basically less. So then you gradually transition into this sphere where the rotational kinetic energy is it's a small fraction of the translational kinetic energy when the sphere is rolling down without slipping. So it only needs to give a little bit of its total energy to rotational kinetic energy, and that means it can translate at a slightly faster rate. So if you were to race all these four objects down the inclined plane, you definitely have a winner with the sphere. And then the second place will be disk, third place will be the shell, the last place will be the ring. Although the values are relatively close, that's because we're talking about a short ramp. The ramp is not very long. If you have maybe a 3-meter long, maybe 10 feet long wooden board, and then you prop it up, then you raise them all down the same board, the distance being longer, the time will scale up, and the difference will make them stand out a little more.